program me here. So what you're looking at here is a neutron star to scale to the Chicago skyline. Yeah, Chicago. Of course, right? Of course.
Second city.
Yeah. Okay, so I just wanted to give you a little bit of timeline of what happened on the X-ray side of the story. We had the detection on gravitational waves, and 0.6 days after the day afterwards, the first two spacecrafts getting on target in the X-rays were Swift X-30, as we heard from Brad, and Maxi. And Swift has been following up the event all the way to 16 days, which is when target went behind the sun, with non-detections. The first Chandra observation was obtained by my team at day 2.3, 2.4 days. It was a very deep non-detection, and I'd like you to bring home this message that even if we got 0 photons, this is extremely, extremely important for the reasons that should be clear afterwards. Another observations by the Goddard team at 9 days, and then another observations by Daryl's Agar team at 15 days, and a shared observation at 16 days with Chandra. And let's see if I could. And this is when we went into sun constraint. The source is gonna be back the first week of December, and we're planning to get back on source. The first detection of X-rays happened at 9 days after the gravitational waves. So here is what we did not see at day 2.3, and here is what happened at 15 days. We have a detection. So I want to make sure you bring home this message. This is the source. Those are 16 photons in the X-rays, and here it is. So this also tells you that this source was very close by, 40 megaparsecs. We have 16 photons, 50 kiloseconds of Chandra, so 7 hours plus observations. So to get a detection, you need at least 5 photons. So you do the numbers, you understand that this is a tough game. It's going to be a tough game in the X-rays, even with the most sensitive machines that we have right now. So beyond 100 megaparsecs, we would be in troubles, basically, with X-rays. And I'm sure that Greg is going to tell us something similar in the radio. He was not right in the radio either. So here is the story. This is the deep non-detection here at 2.3 days. Detection. I'm showing you the data at 15 days because I don't have the data at 9 days. And here it is. And it's consistent. The position is perfectly consistent with the position of the optical counterpart here. As I guess you kind of see, we do also have other sources in the field. This is X-ray emission from the host galaxy, which is also detected in the radio. And the host galaxy turns out to be a weak AGN. And if you're interested, there is a nice paper by Peter Blanchard on the host galaxies. And you might also realize that we do have other sources appearing in the field, in the X-rays. So let's try to put this X-ray emission into context. What you're looking at here is X-ray luminosity versus time for the sample of cosmological short GRBs. And let's put our guy here. And here how it looks like. You have all the Swift X-30 upper limits, and you have Chandra non-detection, detection, and 2 detections here. So you realize already that is way, way fainter, less luminous than the cosmological short GRBs. Very different. So yeah, if you're wondering where is the goal, that is where is the goal. So for our cosmological short GRBs, we were looking down the jet with in our X-rays, and we always have to keep in mind that, as we heard many times during the talks earlier, we might be off axis. So I've been hearing a lot of times in the last few days that the first initial non-detection was a surprise. I don't know why, because in most cases, if anything, we are supposed to be off axis. So the most likely scenario is a non-detection at early times. It's totally expected. It's not a surprise.
Sorry, to chime in there, would you say that's true given that there was a gamma ray detection? I mean, I agree with you if you had no
information about the gamma ray detection was
rays.
orders and orders of magnitude fainter. So than normal short-year B in energetics. So if anything, I would have concluded there is something strange, maybe I'm off axis, so it is even more probable after I saw the gamma rays. So here are the properties that we will try to explain. So we had a rising X-ray emission, and here is the importance of the first non-detection. We detected 0 photons, and then we had 16. If you do statistics, this tells you that the source is rising. This is an extremely important piece of information that is telling you that this source will brighten with time. Another important piece of information is that it did re-brighten, but when we got on target and we detected it, there is no much of a variation of a flux. So there is a mild rise. So most likely we are close to a peak, just because the rise is so flat. The luminosity that we reach is around 10 to 39 erg per second. And even if we have a few photons, we could extract a spectrum, and the two of the three teams agree that the spectrum is kind of hard. A photon index of 1.5 instead of the usual 2 that we find out. Finally, if you put together radio that we hear about from Greg and X-rays, you will find out that both of these wavelengths, they tell you that the slope is around 0.5 in f nu. So those are the features, the properties that we will have to explain, and I'll try to give you some details of what can we do with that. So the picture that we have to keep in mind is that yes, we do something isotropic, the thermal emission that we will hear more about later, and also we might have collimated components. Sometimes we're there, sometimes we're here, off axis. And this is a picture from Wenfei fun, how Wenfei sees highly collimated versus spherical explosions. So let's add Wenfei touch to the discussion. So here we go. So the first question that we asked ourselves was, what if there is a weak jet on axis that is just below our limits? Because we did not get on target earlier than this. So what we did was to take the standard properties of short-year Bs that we observed and try to understand what would be instead the property of this afterglow, of this very weak jet, if that jet was there. And you plug in some scalings. It depends on the position of the X-rays, location of the X-rays in the spectrum, if you are below the Coulomb frequency or above the Coulomb frequency. And here you can see some of the parameters going, density, kinetic energy, and microphysics here, same over there. So you do this exercise, and what you'll find is that if there was a jet that was on axis, and just below our limits, these are the constraints that you would get for the standard densities that we see in short JRBs. So the EK ISO is very low, 10 to 48, or even lower, 10 to the 46, to be compared to what we usually observe, 10 to 51. So if there was a jet on axis, it was way fainter, way less energetic. Yeah.
Which is still comparable with what we see in gamma rays.
So in the gamma rays, you saw E gamma. Your E gamma was 10 to the 47, I think. So yeah. So you can assume a 0.1 efficiency, and you would get this ones. Yeah. So if the jet was there on axis, it was very low energy. So that's a takeaway message from here. However, this component is a declining component with time, so it would not be able to explain the rise. So even if a jet was here, this is not responsible for what we see later. So let's try to explain what we see here. Again, the key word here is rising. So our emission is going up with time. And we have basically two possibilities that we could think about. And the first possibility is that this rising X-ray emission is the onset of the afterglow. So this is the time when your blast wave has transferred most of the energy to the medium. And in this case, we might be on axis, we might be spherical. We do not need to be collimated in this case. Another possibility that we heard many times is just that we are off axis and the relativistic beaming is helping us and the radiation is coming into our line of sight. So I'll go through these two possibilities and try to understand what the two models imply. So let's start with the idea that what we're seeing, this X-ray peak, is because it's the onset of the afterglow. So in this case, we can go back to the GRB literature. The onset time depends from properties of the blast wave, the initial Lorentz factor, kinetic energy, and the properties of the medium where the blast wave is decelerating into. And if you plug in numbers, since we see that these X-rays are rising but not very fast, so we can sort of assume that the peak is roughly around the time when we stopped observing, or maybe a little bit more, 15 to 30 days is the number we assume. We put in the typical densities that we see in short GRBs, 3 to 10 to minus 3, 10 to minus 2 centimeters, -3. And here is where we use the knowledge from what Peter just told us about the fluence that we saw in the gamma rays, and we try to put in an EK ISO for some visual efficiency of 0.1. So we put in this, we plug in all these numbers, and the result, what you would find is that your blast wave is only mildly relativistic. So we can explain this later onset of the afterglow only if the blast wave is kind of started slow. That's the idea. So here the numbers is like EK ISO 10 to the 48 ergs and gamma of factor of 2. So it's a mildly relativistic shock that is going through an environment. And in nature, yes, we have seen mildly relativistic shocks in stellar explosions. And you can see that there are some supernovae that sort of have, and some low luminosity GRBs that sort of have the same parameters. Low kinetic energy and initial Lorentz factor that is kind of low. And for these shocks, we've always seen that the index of the electron density, the electron distribution is around 3, a peak of 3. While here, what we see from the radio, what we would infer from the radio and the X-rays together would be an electron distribution which is more around 2. So I'm not saying that maybe nature doesn't do it, but what I'm saying is that all the mildly relativistic shocks that we know about until now have different properties than this one. Yes?
With the other objects that are in that circle, are any of them near enough that you would expect to see gamma rays as well?
The supernova, you mean?
Yeah.
So we did the search with the IPN network. So those are short GRBs, sub-energy GRBs, so yes, we do have gamma rays here. Well, sub-factory. But for these ones, we did the search, we didn't find it, but we were not covering the sky at 100%, so there is space for not finding anything. So I was saying that the SCD of this particular of this shock is different from what we see from other mildly relativistic shocks that we know about in nature. And here is another way of looking at it. You have X-rays here and radio, and here I'm plotting different SCDs based on the distribution of electrons. And you can see that what you need is a P of the order of 2.1, 0.2 is what you need to put together the X-rays and the radio. And they're on the same parallel. That was the other important piece of information. So let's go to the other possibility. So what if this is not a mildly relativistic shock going through an environment, but we're just off axis. Relativistic, collimated, but we are just off axis. And in this case, the radiation would reach us whenever the blast wave decelerates enough so that the beaming, relativistic beaming is not so severe. So here is the idea. So the first, I'm going to do this. So first, I'm going to be using a couple of analytical scalings to understand roughly where we will end up with our modeling. And then I'm going to be using the fantastic box fit code that Andrew just told you about. It's a fantastic tool, Andrew. Thank you so much for you and your group for doing that. First of all, peak time. So in this case, the peak time has this very nice property that doesn't depend on microphysics, which is a huge question mark for us. So the peak time, the time of the peak, speaks to the kinetic energy of the blast wave, the density that the blast wave is encountering, and the angle at which we are. So again, we can plug in some typical numbers just to have an idea of where we would go. And so if you take a very, very generous range for peak times between 50 days and 70 days, this is what you get. And if you put in the typical EK ISO of EK, in this case, of short GRBs and typical densities, you would end up with a range of observing angles, which is between 20 and 40. So this is just from a very, very back of the envelope calculation of what the peak time is telling you. And this is the data obs. When instead we start considering the flux, the actual flux and luminosity we saw, then we have to plug in also epsilon B and epsilon E. This is very unfortunate because we don't have a good knowledge of which number to put here. So this is when we used Boxit, and we simulated a wide grid of off-axis GRB jets. And you can see the range of EK ISO that we generated, the range of densities. This is us going at more and more off-axis, a range of epsilon B's, range of epsilon E, and P, we limited ourselves to these two values because we knew that otherwise we would never be able to explain the radio. And then we ran our simulations for two jet opening angles, a very collimated one and a less collimated one. So as you will see, this model has, the parameters are highly degenerate. So there is a family of solutions. There is not such a thing like a solution, it's a family of solutions that we could find. And here you can see, I just plotted here an example, and then I'm going to tell you about what the entire simulations are telling us. So what you're looking at here is X-rays versus time, same jet with these properties here, and at different angles. And you can see that we prefer, for this particular model, we prefer 22 degrees off-axis angle. And here you can see instead the same jet at 22 degrees at different wavelengths. So you can see the X-rays, you can see the R band, and here I just wanted to take away this point that this off-axis, the afterglow and the optical, is always way less luminous than the kilonova. So in no way it would be a problem. And then there is here, just plotted here, the 10 gigahertz light curve. So I told you there is a family of solutions. Yes?
Would any of the results change if you use the constraints on the observing angle from the gravitational waves?
Later, because the game I want to play is to constrain H naught.
Oh, okay.
I want to play the other game.
All right.
So this is a family of solutions that we find. We end up with densities between 10 to the minus 2, 10 to the minus 4. EK, this is not EKI, so it's EK, really, correctly for beaming, between 10 to the 48 and 10 to the 50. And our observed angles are between 25 and 50. So there is a wide range of solutions that would be able to explain this data set. So as the next step, Monday, after all the data came out, we did this exercise to put all the data together, including the data that Greg is going to tell you about, and we rerun our simulations and our fits. What you're looking at here is the same thing where I put together all the radio and all the X-rays, and you can see, you can take away one point here, is that as it is right now, we always fail to reproduce the initial X-rays and the initial 6 gigahertz detection. To me, that might imply a structure in the jet. A structured jet would give you for free a brighter emission at earlier times. That said, I also believe that the only way to find a solution is to wait and see what is going to happen at later times. And again, this is the family of solutions that we found.
So,
Yeah.
sun constraint will correspond to
100.
100, okay.
Yeah, well, radio is not constrained,
Yeah.
so they're observing, right, Greg? And we're observing ourselves also into the and this is the X-rays.
You
Chandra.
won't, so this is where you won't be able to detect it, maybe get with it.
For this specific model,
Okay.
maybe not, but like if you go here instead, it's totally doable. So it actually is possible. And XMM will also be available in, I think in December as well. The problem with XMM is the larger PSF, so you would suffer from contamination from the host and the other two sources. So it's not ideal. So let's put this thing together with the kilonova colors. So we heard already that the kilonova showed blue colors, and Matt is going to tell us more in the afternoon. But the fact that we did see some blue properties is telling us that most likely the theta ops is lower than maybe 45-ish, something like that. And so if you put together these two constraints, so those are our family of solutions. And these are the colors. You can see that we are consistent. So going back, this is just to tell you to stay tuned because X-rays and radio are not over. The source is still on there, and we will be on source in December in the X-rays. So as the last thing that I wanted to say, that's a big question I really want to answer to, is related to your question. So earlier today, we played the other game of using our knowledge of H naught to understand the inclination angle. And I like instead playing the other game. Just because we do know we have a problem with Planck and shoes. So the game that we tried to play was, okay, this is the degeneracy that you get if you only analyze gravitational wave data. So you have inclination here and H naught here. What if we would plug in our constraints from the modeling of the off-axis emission and see how we would improve or not improve this kind of thing. It's mostly proof of concept, but it's just to show one possible way to put everything together. So this is what we did. And if you're interested, the paper came out on Wednesday, no, Tuesday night. So you have here let's see, you have Planck and shoes here, and then you have the dashed line is what comes out from the gravitational wave analysis. And then what we did was to revise a little bit the peculiar velocity, the assumption of peculiar velocity on the host galaxy. And it is why we get basically the same uncertainty on H naught that you can't read it. But here what we're doing is we're putting in our probability distribution that we got from our fits on theta ops. And the dream would be to combine this knowledge to get a better constraint on H naught based on our modeling. And here you see the results in green and blue. Since we put in a larger peculiar velocity of the host, we actually end up with the same uncertainties. But if you were to use the same assumption of peculiar velocity, even if our constraints on theta ops right now are not that great, we'll be able to cut down the uncertainties of a factor almost 2. To put this thing into perspective, we would need, based on gravitational wave data only, we would need something like 70 of these events to be able to go down to be able to say who is right. And if you put in the constraints from this event at this point, without putting in the future knowledge, we would need something like 50. What I'm hoping is that using data that we will get at 100 days from now, we would really able to constrain this much better. So the actual constraint on H naught will improve. So this is just a proof of concept of how to use this event on H naught. Yeah.
So we should not take away the message that higher values are preferred.
Well, It moves, so it's totally true that we move, but it's not statistically, it's not that the uncertainties are huge enough that you would still go with both. But it's true that if you plug in the constraints from the modeling of the Dolph axis jets, then you would move the ticket higher. That's true. Yeah. To be totally fair, these constraints are model dependent because they depend on the structure of the jet that we put in. They depend on on all the assumptions that we put in jet simulations. So that's totally true. And that's all I wanted to say, I guess.
Two questions, Lynn?
Where does your revised estimate for computing motion come from?
So my two colleagues, Dan Skolnick and Dylan Trout, are a little more conservative, and they decided that they felt safer in putting in more ignorance on the peculiar velocity of the host galaxy based on our current knowledge.
It's not from a specific peculiar velocity survey,
I don't remember. I should go and look into the details. Yeah.
Brad?
Can you go back to your model fits for a second?
This one?
Yeah, these are great. Perfect. So, I mean, my recollection of the box fit code, and Andrew should correct me if I'm wrong, is that it starts out with like an initial Lorentz factor of 200 or 300 for the blast wave. And in Peter's talk before, he just said that, for normal top hat jet, in order to get a reasonable gamma ray luminosity, you can only be a couple degrees outside the jet opening angle.
For a top hat jet.
For a top hat jet.
Yeah.
Which is what that is. So, I mean, is it possible to find a solution in your family where you're like, just outside the opening angle that would give you a consistent picture with that?
I think that you would need to broaden your jet opening angle. I think that you need to widen this up, and then you might find your solution. Yeah. But at the moment, I would say that what you find from BoxFit is that you would prefer wider jet opening angles, but you can find a solution almost everywhere. It's true that if you start to play with the jet structure, you would modify this part, but not this other part. So maybe.
Any other questions? One for Zoltan while Greg gets that set up.
Just for fun, but the last exercise, first congratulations.
Thank you.
People could become cosmologists. So the assumption is the jet is, so one measures the jet angle, the other the gravitational wave.
It's inclination, yeah.
What is, maybe this will come up in the theory section in the afternoon, but what do we know about the visual angles?
The angular momentum and the jet. So that's the question is how.
I don't know. That's Andrew.
Yeah, the assumption is that the angular momentum and the jet are aligned. Yes.
So your angles are.
I say again?
Yeah, your unstated assumption was that the jet angle is perpendicular to one.
Yes, absolutely true.
How much do you know?
Depends on that.
I mean, again, we do expect most of the momentum of the black hole to be in the same plane as the disk, so I think it's reasonable.
If you look at a pulsar, it's not the case, right? It's way off.
What's not the case with the
Well,
pulsar?
I mean, if the magnetic field is misaligned with the spin, then what is it doing with collimation?
Yeah, we think the accretion disk is providing the collimation, or this environment that's carved by the dynamical ejecta, as Andrew said. So, yeah, it's an assumption, but it seems reasonable. So, okay, let's thank Raphael again.